Hello. Today's video is going to be on input shaping. Some people call it sway control or swing control, but I'm going to use the term input shaping. And what input shaping does is it is used in crane and other type of applications where the load is swinging. In other words, it could be something that will vibrate, or in the case of a crane, you could be moving the crane back and forth, and then you have the load down below and it can swing. And the point is that you want to move into position without having it oscillating after it gets there, because the oscillations can be dangerous. Also, the settling time will just make the production, moving back and forth, slower. So to start with, what I'm going to do is first model the crane and then model the load. And both models are going to be fairly simple. To begin with, I'm going to start with, this is the crane. I'm going to just assume that it's got a gain and a frequency, which is the inverse of a time constant. And then I'm integrating the velocity to position. Got a PID controller, and I'm going to calculate the gain symbolically. I'm going to go through this quickly because I have another video that shows how I do this for a simple gain and an inertia load. So I've got the calculations for the crane. What I am doing that's kind of cheating a little bit is I'm assuming that the crane has enough power such that it's not going to be affected by the load, because when you're pulling the load quickly, the load's going to be behind, and then when you slow down, the load's going to try to pull the crane forward. I'm kind of assuming that the load is not going to have much effect, if any, on the crane. Now we have to do the simulation for the crane, and that's a second order system and underdamped. Oops, it loads down here. And I'm assuming that the system's got a damping factor of 0.01. I don't know what it really is with air, and I know when you're just moving back and forth with air, it's actually proportional to the drag is proportional to the velocity squared, but that requires a lot of differential equations, which would complicate this the point that I'm trying to get across. So I just assume that it's relatively linear, and the same goes for the cable length. There should be a sign factor in here. So this is the natural frequency based on the length of the cable. You got gravitational constant, or this is the acceleration due to gravity, and this is the length of the cable. So that gives us the natural frequency of the oscillations in terms of radians per second. So I have my discrete or my continuous arrays. I'm calculating discrete arrays, and now I'm getting to the point that I want to show you. Now, about input shaping. There are other videos that actually show how it's done, or they show it being done. But as far as I know, I'm going to be the only one that shows how to calculate it. And the goal here is, like I said, is to get into position without having the load oscillate. And the way that you do that is that you have the velocity profile, and you use half the velocity profile to start with, and then you delay half a oscillation wavelength, and then you do the other half of the profile, and there's going to be a point in the middle where you sum them together. But basically what happens is, because you're issuing half the motion profile twice, but 180 degrees out of phase, the second motion profile cancels out any oscillations caused by the first motion profile. So what I have to do is I have to calculate out two impulses. This is the coefficient for the first impulse, is the coefficient for the second impulse. And like I said, you're using half to begin with, then a half of the motion profile in the at half a wavelength. But it's not quite half. You can see that there's a slight difference here, and the reason why is because there's a damping factor involved. So the damping factor, the damping of the system is going to make it so that the second impulse doesn't have to be as big as the first one. So where do these coefficients come from? Well, I've got this Q0, that's the first coefficient. I got Q1 for the second impulse. And I just used 1, that's kind of arbitrary here, but I just used 1. And then this is how much the sine wave is going to decay over the half wavelength. So, and where does that come from? Well, if we take a look at this, there's a damped frequency of oscillation, which is, you can see here. And where that comes from is if I were to do a step input to a second order system with it's underdamped, I get a response that looks like this. This is all symbolic, and you can see that you have to rearrange the terms here, but this part here is essentially this, and then you can see the scroll over here a bit, and this minus zeta times omega is what you have up here. Now, what you'd have to do to make this look like what you have down here is have an omega up here and an omega down here, and this would be the damped frequency of oscillation, and this would be this time constant at 1/2 a cycle. So this is the two coefficients, and the denominator is just the sum of this plus this, so that the two terms will add up to 1. So hopefully you can see where the coefficients come from. I'm going to skip by this real quick. Okay, to start with, I'm going to assume that we have a max speed of 3.6 meters per second, and that's 90% of the maximum velocity of 4 meters per second, and I'm going to have a set point of 10 meters. Now I have this is the length of the sample time, which is basically the time it takes to make the move, and then I add a cycle to that. So the shaped velocity function is basically implementing the when to add well, you're multiplying the coefficients times the max velocity. And I'm assuming here that the velocity or the motion profile would be normally just a straight motion, no accels, no decels. The accelerations and decelerations don't make that much difference. So I just assumed that I was going from point 0 to whatever the set point is at a fixed velocity. But what I have to do is I have to multiply this velocity times the max velocity if the time is less than the move time. And then what happens is that if it gets past 180 degrees, or that halfway point in the wave, then what I have to do is add the second impulse. And then that's going to last for a move time. So down here, I have the actual implementation. So R is my where I should be. I have my crane position and velocity, the control output, and the load position and velocity. And I start with my position being equal to 0, and I calculate out the velocity, and then I have to integrate the velocity to become position. We'll get back to this again. This is updating the position and velocity for the crane, and then the position for the crane is basically the input to the position for the load. I have the error. I have the PID implemented here. So now you can see the two impulses. The first impulse is here, and then it doesn't move, and then the second impulse is here. So you can see the position increasing, and the position increases at a linear rate because I don't have any accels and decels, and then it just abruptly stops. And then you can see that it carries on until I get to the set point of 10 meters. The red line is the crane position, and it's using the PID to follow this target, this shaped input. And you can see that it lags behind a little bit because I'm not using feed forwards, and I don't have the gains cranked up very high. I told it to have the poles at basically at 1 hertz. So if we look at the velocities, you can see that the two impulses. You get one impulse here, and then that impulse dies out, and the second impulse starts, and then it dies out. And so you can see that the motion, this is the crane. You can see that it gets to the set point, and then it starts to decay, and it gets up to the set point again. But this is the velocity of the load, and you can see that it lags behind at first, and then it swings ahead, and then it swings back, and then it gets exactly to 0 at the very end, just like the position up here. You can see this is the load position, and it goes into position. So here it's falling behind by quite a bit, and then during this time when it stops, you can see the load starts swinging ahead, and then the second impulse begins, and then we cancel out the oscillation, so it stops right at 10 meters like it should. So let's go back. And again, we have the shaped velocity, and that's what's generating that magenta line. The position is just integrating the velocity. We have the target position and velocity. This is using the target position and velocity to generate the crane position here, and then we have the crane position from here as using it as an input to the second order equation for the load. We have an error between the crane position and the target position, or the shaped position, and then we do the PID again, and we return the target or the shaped positions and velocities, the crane position and velocities, the control output, and then the load position and velocity. Now, this is good, but what is better is to use 3 inputs. It's much more robust. And again, I'm using the same parameters as before, but what I have is 3 inputs, 3 impulses. I have one at the beginning, one at a half a wavelength, and then one at the full wavelength. And you can see that the difference here is I'm starting out with 1 here. This is this would normally be this omega times zeta times pi, which is half a wavelength. You got to remember there's a natural frequency here, but they cancel out. And then this is at 2 pi. So this is at the beginning of a wavelength or an oscillation. This is at the halfway point, and this is at the end. And the way that I weighted these is that this is 1, and then this is 2, and this is 1. So that way you have 2 at the 1 at the beginning, 1 at the end, and 1 twice as big at 180 degrees. That should cancel out the 2. So again, this is the same function as above, except for I have yet another impulse, and this one happens at 2 pi as opposed to pi. This function is identical to the one up above, and you can see the results here. Let me just stop this for a second. You can see that this is the shaped target generator. This is the crane position. This is the load position, and it gets right up to 10. And you can see that there's 3 different impulses. And let's look at the velocity. And it's easy to see the 3 impulses. 1, 2, 3. And you can see this is the load velocity, and you can see that it gets down to 0. I should have probably extended the graph out a little bit more so you can see that it doesn't oscillate at the end. But it doesn't. So what I'm going to do now is I'm going to change the distance that it's moving. So I'm going to change the set point up here to 20. And this is the 2 impulse wave shaping. And you should notice that when it gets to be long enough, the crane position and the load position match exactly. They match here also on the velocities. So once you get to a certain point or a certain distance, what will happen is that there's a canceling out of the oscillations that occurs here, and then the target position for, or the actual position for the crane and actual position for the load end up being the same, and there's no swinging whatsoever while you're moving it. Let's see what it looks like for the 3 impulse. For the 3 impulse, it's a little bit different. You can see that it's not matching the velocities, but in theory this should be more robust. It's not oscillating, but you can see that it's not following the, it's not moving at the same velocity as the crane. So there's a difference between the load velocity and the crane velocities. So let's now look at it for a shorter move. Go back up here, and we will just make this a 2. And you can see the 2 impulses here, 1 and 2. And you can see the crane position, and then this is the load position. It just makes one gentle swing. Same there. And let's go down and take a look at the 3 impulse version. You can see that there's a few more waves in this one, and you can see the velocities here. So the key, going back up to the equation, is these coefficients that are used to generate the impulses, or in a way you can kind of think of it if you had a convolution or a filter where you have different taps, and you're tapping off of stored velocities or calculated velocities at certain time periods. In fact, if you were doing a crane, you would probably have someone with a joystick, and as he's moving the joystick back and forth, the position of the joystick would be proportional to velocity. And that would be saved in a queue, and what you'd have to do is use these coefficients to index into the queue to pull out the velocities at this impulse and for this impulse. So it's possible that you can have just totally arbitrary motion profiles, and yet you're going to be able to move the load from one point to another without having the oscillations. And if you take a look at the videos, you can see them try the different numbers of impulses, and it's very easy to see the systems kind of move, stop, move, and stop, or move, stop, move fast, and then stop. And that all depends upon the distances that they're going to move, but it's really very apparent in those videos if you know what you're looking for. And again, there's no magic here. what we're doing is we're looking at, well, this down here is just a simplified version of this equation. And this comes out to be 1, and this is the damped frequency of oscillation that gets multiplied by the sines. That's what would be here. And this zeta times omega t determines how fast the amplitude of the swinging is going to decay. So that information is used to make these two coefficients, or if you're going to have more coefficients, you can have different fractions of of an oscillation. In other words, you could try using 1/4 or 1/2 pi, 1 pi, 3/2 pi, and pi, and have 4 impulses within one wavelength. I haven't tried that yet, but I bet it would work just fine. Anyway, that concludes my video. Make sure that you take a look or do a search for input shaping on YouTube to see real systems that do this. The main purpose of this video is just to show the math that is behind the input shaping. Bye.